Now please don't take it personal. Don't take it personal. But I gotta go and work. I gotta go work. You know what I'm saying? And I know deep down it hurts. I know it hurts, but I'm a blue collar worker. Now it's a long road ahead of me. Eyes wide open, trying to rock my flow steadily. I'm trying to stay focused so these bras don't get to me. But dog, you get.
Hello and welcome to the practice problems video for integration using polar and spherical coordinates. I only put polar and spherical because I won't be doing an example on cylindrical, but it is closely related to polar, so I think you should be good with that. Okay, so let's see. Our first example is going to integrate the following. So we're going to integrate f of x comma y over d using polar coordinates, so polar. And I'll abbreviate, polar coordinates. So we're given f of x comma y equals x times y, and our d, our domain, is the following. X is greater than or equal to 0, and y is greater or equal to 0. And then we also have x squared plus y squared is less than or equal to 4. Okay, so first of all, in any of these problems, when we're doing double or triple integrals, they usually won't tell you, at least on tests anyways, to use like, this is when you're going to use polar, or this is when you'll use cylindrical or spherical. They'll just expect you to know somehow. And, I mean, even I can't, like, after going through this course and several others, I can't just, like, look at a problem and be like, oh, yeah, I know what to use. Not automatically anyways. I find it helpful to draw pictures, just because pictures help you visualize what you're doing and why. So let's graph this thing. So this is a circle of radius 2. So I'm going to attempt to draw a circle again. We all know how that turns out on here. So anyway, so this is a circle of radius 2. So we're going through 2 here, negative 2, and negative 2. Okay, so this is our x and y. Alright, so this is on the xy plane, and also D isn't the entire circle because we have these restrictions here, which mean that x and y both have to stay positive. Stay positive, yay. So that just means we're restricted to the first quadrant, okay? So D is essentially this thing, alright? So the shaded, so that's our D, and I'll enlarge it a little bit so we can study it a little more carefully. So we have something like, that looks like this, okay? And it crosses through 2 on both of the axes. And, okay, so that's our domain here, right there. So looking at it, we can determine that polar is a good option because our radius ranges from, 0, that would just be the point here, all the way up to 2. Right? Because the radius is the outermost, or the upper bound for the r is going to be a constant 2 because we're dealing with a circle here. So basically, it needs to go from, r goes from 0 to 2. So that means that if r were anything less than 0, that means it would be going this way or something. I don't even know what that means. I think it just means it goes out of the region, which is, yeah. So if it goes backwards, it's definitely out of the region. And if it goes higher than 2, like over here, that's definitely going out of the region as well, right? So it has to stay within 0 and 2, okay? So that gives us the radius, and now we need to determine the bounds for theta, the angle. How much are we rotating here? So we start at 0, so theta equals 0 is the x-axis. So we're starting there, and we rotate all the way up to the y-axis. And at this point, our theta equals, straight up and down, so pi over 2. So it goes from 0 to pi over 2. Okay? And then the other thing we need to keep in mind, so we found the intervals. That's good, the bounds here. And we also know that x equals r cosine theta and y equals r sine theta. These are just important for plugging in to the given function, the f of x comma y. Also, the last important thing, when we're switching into polar, is that our differential area is now r dr d theta. Okay, and don't forget that r. Remember, we just learned that that's the Jacobian. So, Jacobian, yay. Okay, so now let's set it up. We have the double integral over d of f of x comma y dA equals, now we're going to do our change of variables. So I'm going to write the theta bounds first. So 0 to pi over 2, and then this will be d theta at the end here. Okay, and then we have our r bounds, 0 to 2. So this is dr, and don't forget the r right in front. Okay, and now we're going to plug in our x and y. So we're going to plug in r cosine theta for x here. So that'd be r cosine theta. And this is times y, which is now r sine theta. R sine theta. Okay? And this is the complete setup for the double integral. Okay? So now we can just simplify things. And I'll do so on the next slide. So we have 0 to pi over 2, and then 0 to 2. And then if we combine all the r's, we get 3 of them. R times r times r. So r to the third, and then cosine theta, sine theta. And this is dr d theta. So as we can see here, we're at a point where we have an iterated integral. Iterated. So we're going to group all the r's together. So let's get the r bounds. So we have 0 to 2, and the r to the third, and dr. So that's all the r's together, and all the theta things together. 0 to pi over 2, cosine theta, sine theta, d theta. Okay? See there, we just separated everything. And now we'll just solve through. So this first thing is 1 over 4, r to the fourth. And then, oh, hold on, little line here. So r goes from 0 to 2. Okay? And then here we'll have, so this is, we have to recall our trig identities. So what we actually have is, remember how 2 cosine theta sine theta equals sine 2 theta. So this is our double angle formula from maybe trigonometry in high school, I think, something like that. So this is our double angle formula. Double angle formula. Okay, so basically, to get cosine theta, sine theta by themselves, you just divide sine 2 theta by 2. Okay, divide both sides by 2, and you get that by itself. So what we're going to have is plug this in for cosine theta, sine theta. So I'm going to, I guess I'll just write it like that. 0 to pi over 2, sine 2 theta over 2, d theta. Okay? And then what we'll have is here, when we plug in, so we have 1/4, and then 2 to the fourth minus 0. And then here I'm going to bring out the 1/2 in front, just to make it simpler and easier to look at. So then we have same bounds here. Then we have sine 2 theta, d theta. And what I'm going to do now is actually a u substitution. So I'll make u be 2 theta, alright? And then du, taking the first derivative of that, we're going to implicitly derive. So we get 2 d theta. And then to get d theta by itself, so I can plug it directly in, divide by 2 on both sides, and we get that d theta equals du over 2. So I'll plug that in on the next step. So we have 1 over 4 in front here, times a 16, okay, and then we have a 1/2 from the double angle formula, remember? So then if I employ u substitution, we get sine u inside here, and d theta now is du over 2. du over 2. Okay? So at this point, now we can just bring the 1/2 outside here. So I'll try to squish this in. So this turns into a 4 in front. So then we have a 4 times 1/4. So that would just be 1, right? So 1 times sine u du. Alright? So now at this point, we just integrate like normal, and I'll continue that on the next slide. So the integral of sine u is negative cosine u, and there's just a 1 in front. And then at this point, we'll just plug in 2 theta for our u, and then reinstate our bounds. So negative cosine 2 theta. So this is a double angle, right? And then our bounds for theta were 0 and pi over 2. Okay, so then we're just going to plug this in and solve for the rest. So we have negative cosine 2 times pi over 2 minus a negative cosine 0. Okay, so these will turn positive, and we get this is cosine pi, so that would be a negative 1, so a positive 1 plus a positive 1 equals 2. And 2 is our final answer. Okay? Alright, so now on to...
Now he's meaner than meaner. Was sweet, now he keeps his heart next to his Nina. And you used to see him saving up his money from shows to get her a rose, turning down ridiculous hoes. All he wanted was a chick with his